Yes. The K-map is used to it's used to simplify so this equation has 5 terms and it has 4 variables. Because it has 4 variables. The same as truth table, you need to list all the multiple values. 0, 0, 0, 1, and 1, 1. Now 1, 0 is 1, 1, and 1, 0. Y is 1, 0. There is 1, 2, 3 from 1 row to its neighboring row. So in this way, you can have a sort of map. And then you can write the corresponding term box. For example, the first term is A bar B. So in order to identify which box, the first term should be in. You just need to consider how this term one. So in order to generate a 1, A has to be 0. And the other variable in the first term, Y, only A has the bar. And then this term actually is related to 0, 1, 1, 1, 3 ones, 1, 0, 3 ones. So it's a 1, 0, 1. So this box corresponds to the first. The second term is 0, 1, 1, 0, 0, 1, 1, 0. The third term is 1, 0, 1, 1, 1, 0, 1. And then we have 1, 0, 0, 1. The last one is a 1, 0, 3 zeros. So after you have this, after you have all the terms in this box, you need to use these rules to cover all the ones here. Use as few circles as possible. Cover only once. And the size of the circle has to be 2 to n. N can be 0, 1, 2, 3, 4. So the number of the size of the circle can be 1, 2, 4, 8. And then the circle has to be as large as possible. So apparently, I can draw a circle like this. I can also draw like this and this. Can I group these three together? No, I cannot. Why? Because the size of the circle can be 3. It has to be 2, 4, 8. So in this way, I can cover all the ones in this map. Then I need to write these 3 circles into back to the equation. For example, this one. For this one, A is always 0 because this one is a 0, 1, 1, 1, 1, 0, 3 ones. For this one, it's a 0, 1, 1, 0. So for these two, A is always 0, B is always 1. C is always 1. D can be 0 and D can be 1. So if one variable is 0, 1 concurrently in this circle, then you can remove it. Then if this circle indicates this green algebra term. And then this one is A, B bar. C is always 0, C bar. D can be 1 and D can be 0. All right. The last one, which is A and B bar. Because A is always 1, B is always 0. C can be 0, C can be 1. So you have no C and then D. Question. Each step. Yes. Yeah. Yes. Yes. You mean give it this one, but only one circle?
No, not if we only want to having one circle. Still
draw the circle as large as possible. Right? So cover all the ones is the wild circle, but the other rule is draw the circle as large as possible. Let's do something like what you said. If, for example, you just give this single one a circle. This single one here indicates A, B bar, C and D. So it's this term plus this term plus this term. So you can see which expression symbol. So this is why we want to draw the first one. Apparently, the first one is the one. You don't have to get the D. You don't need the D at all. Any other question? So I think you can expect a similar question. If there is a problem, is about the Any other question? Yes. Yes, you have no problem with that. But I would like to walk through this problem. So, I give you for the equals here. There are two steps. The first one is to draw the pull-down method, and the second one is for pull-up. Pull-down method is of course you don't have this equals here. In the pull-up method, equal circle. So in order to draw the pull-down method, the pull-down method actually F bar. So in this case, the F bar is A plus B. C plus B. It's actually this. So and then we can start to implement this one. So because C add B, so actually C and B like this. So they are parallel. They are connected in parallel. And then you have the multiplier and B. So you can draw B here. Or you can draw B here. It doesn't matter because they are sequential. So in this figure I draw on the top of C and B, but here you can draw B like this. And then you have you have all of A. So A can draw here. You can draw A like this. Or you can move A to this side. It don't matter. The only thing you need to notice that is that this component, the large component here, and they are connected in terms. So this is how we handle the pull. Now, for the pull-up method, we need to apply the actual implement that, but we need to apply the so-called De Morgan law. So this is the first step. And second step. And this is the So because for the P modes, we have a little circle. So it indicates not. So in order to implement this C bar and E bar, right, this component. And then this is all. And then secretary. Of course, connect these together. Any questions? So I don't think this problem, this problem is follow the steps here. The first one is to implement the F bar in the pull down method. Before that, you need to apply the De Morgan law. Any question? Yes. Well, typically we write the block number, but the ground here in the pull down method. Any other questions? So in last lecture, some students asked me about this power and the power efficiency. So I think the most important in this equation is not slope. So if you can understand this law, I don't think you have any problem with the examination. So this law is used to implement, is used to help you identify where is the bottleneck and compute what if you have, what's the speed up. So one example will be if the R is 80%. So if 80% of your application is a floating point operation, floating point operations, and if you can buy a new floating point unit. What's the speed up if you have that unit? Assume that unit is 10 times speed up. So what's the speed up for overall application or overall system? So in this case, you need to use the unbound flow. So among this 80, for this 80%, these 80% are floating point operation, and 20% are non-floating point operation. So your new floating point unit cannot help this 20%. But your new floating point unit can reduce this 80% to the latency is 80% to 8% because you have a 10 times speed up. So when you sum these two terms together, this is the new time. And the original time is of course the 1. 1 operation, 20% non-floating point operation. Non-floating point operation cannot benefit anything from the new unit, but the new unit does improve the floating point operation performance by 2%. So you use this 80% divided by 2. And then you can have the speed up. And this equation is named Amdahl's law. I think you understand. Any other questions? So if I ask you to compute the power consumption, I will provide these equations. All you need to do is just plug these numbers into the equation and compute the values of the power. And if I ask a question about the yield, and how many die you can fabricate on a wafer, I will also provide these 3 equations. Yes. This value is actually standard. I did it, but I didn't show the procedure. So this slide, so these two are different questions, but they are the same. Both of them in the examination. So in the examination, if you do not know the equation, you can ask me. I will try to list the equation, attach the equation to the problem on the examination paper. So you don't need to recite these equations, but you need to understand how to use them. General. Ten or 11. But no. If no question, you can stop. If you have more questions, you can ask me